Hey everyone, Mr. J here. Welcome back to Chem Talks. Today we're going to talk about something called the mole. And when we talk about quantitative chemistry, the mole is probably the central concept that kind of links everything together. So it's a really important concept to make sure that you understand. It's not a hard concept, but it allows us to do a lot of things. And the mole is simply a measure of counting, kind of like if we say a dozen, we mean 12 eggs. When we talk about the mole, we're talking about a specific quantity of atoms. And once we know those atoms, then we can relate it to the mass. So let's go ahead and start talking about the mole. So the first thing we have to talk about is a gentleman here by the name of Amedeo Avogadro, the handsome-looking gentleman there in the picture. And Avogadro was an Italian physicist and professor, and he originally worked with gases, and he came up with what is known as Avogadro's law, which we'll talk about in just a little bit. But his work with gases laid the foundations for the mole. And what he kind of linked was this idea between the mass of an atom and how many particles are in that given mass. And this is where the mole came out of. And so Avogadro hypothesized that equal volumes of gases that are at the same temperature and pressure, what we call STP, we'll talk about why in a later unit, but understand right now that the gases have to be at the same temperature and pressure. If they have the same volume, they're going to have the equal number of particles. And STP conditions are 0 degrees Celsius and 1 atmosphere, and we'll get into that later towards the end of the year when we talk about gases. But this idea came to be known as Avogadro's law, and this was the basis of the mole, which we'll talk about here in just a little bit. Okay, also known as Avogadro's principle. Okay, just a little review of things we've already talked about previously. We have the term atomic mass. Remember we talked about this in our structure of atom unit, and the atomic mass is just the mass of one atom. Technically, we know it's the weighted average of all the isotopes of an atom, but it's basically what's the average mass of one atom. Okay, and we measure it in AMU, atomic mass unit. For example, hydrogen has a mass of 1.01 AMU. We can then also talk about what we call the formula mass, and the formula mass is just how much, or the total mass of one molecule of a substance or one compound. For example, if we add 2 hydrogens to 1 oxygen, we get a total mass of 18.02 AMU. But as we talked about, that AMU is a really small number. We can't put one molecule of water on a scale and weigh it out. We don't have anything yet sensitive. So what we do, like we said, they're not very useful. So what we have to do is find a way to take the mass and make it useful. And that's what the mole does. It's going to relate the atomic mass in AMU to grams. So we have a way of converting kind of from mass to grams, or getting enough of those molecules so that we can actually weigh out in a scale. Okay? And the term we use in chemistry for this is an Avogadro's number, or a mole. Now, Avogadro's number wasn't created by Avogadro, it was instead named in honor of him. So let's talk about his number. And so all Avogadro's number is simply a measurement of the amount of particles in a substance. It tells us how many water molecules are in X amount of grams or something like that. We can calculate from it. And as I said, it's named in honor of Amedeo Avogadro. He laid the groundwork with his work on gases that allow us to do this. And our definition of his number is the number of atoms found in 12 grams of carbon-12. They reference it to carbon-12. If you look at carbon-12, it has a mass, I believe, of 12.00. So in 12 grams of carbon-12, what we find is there's 6.02 times 10 to the 23rd atoms. That is a giant number. And that number right there is Avogadro's number. So that's a number you're going to have to put in the back of your head and have memorized. Okay, so one mole of a substance, we'll say, has an Avogadro's number of particles. Okay, so a substance contained in Avogadro's number of particles is called the mole. We abbreviate it MOL. Okay, not much abbreviation, but it's a little something. Okay, the term mole is Latin for being a heap or pile or a lot of something. That's where the term comes from. And so any 1 mole of any element or any compound contains 6.02 times 10 to the 23rd particle is probably a better term than atoms. Particles is atoms, or it could be molecules, or what's called formula units as well. And what this number allows us to do is establish this relationship between atomic mass and grams. So we can get out of the AMU and start measuring things in grams and being able to tell how many particles we have. Okay, we can also use it to convert between things like number of particles and number of moles. So there's a lot of stuff. Just to give you a little FYI concept of how big this number is. If we had a mole worth of pennies, okay, we can do what's called dimensional analysis, which we already talked about here, and figure that in, okay? What we'd find it's 6.02 times 10 to the $21. That's a lot. Now, if we spread that wealth over the human population of about 7 billion people, roughly, okay, that means each of us would get 8.6 times 10 to the $13th. That's a lot of money. So you can understand that it's almost hard to grasp how big this number is, but it's huge. So let's go ahead and talk about how we can use the mole. One thing we need to get into, talk about a little more detail, is subscripts. Now, when we talked about subscripts of molecules, we said if we have H2SO4, sulfuric acid, in one molecule of it, we had 2 hydrogen atoms, 1 sulfur atom, and 4 oxygen atoms. However, when we talk to moles, those subscripts are no longer single atoms, so they become moles. So in 1 mole of H2SO4, we have 2 moles of hydrogen, 1 mole of sulfur, and then 4 moles of oxygen. Now, if I had 2 moles of H2SO4, I'd double it. So I'd have 4 moles of hydrogen, 2 moles of sulfur, and 8 moles of oxygen. Okay? So that's going to be important to remember as we move through this unit. All right, so a term we're going to use rather than atomic mass or formula mass is molar mass. And molar mass is simply the mass in grams of 1 mole of a substance. So whether that's a atom or a compound of some sort, we can use the term molar mass. Other terms you might hear thrown around are things like gram atomic weight. Okay, gram atomic weight is the weight of 1 mole of an element. The other one you'll hear is formula weight, and it's weight of 1 mole of a compound. Okay, well, we're going to combine those for our purpose and just use the term molar mass. It makes it a little bit easier there. So the molar mass, when we're using it, what we want to do is round off all weights from the periodic table to do 2 decimal places before doing any calculation. So anytime you go up to take a number off the periodic table, remember our molar mass number or our atomic weight number is now going to be the decimal number, but we want to round that to 2 places just to kind of standardize it for our class. Okay. So if we look up oxygen on the periodic table, it has a molar mass of 15.9994. We're going to round that to 16.00. So please do this every time. It'll make it a little bit easier for everybody if you do this. Okay, so let's talk about how we determine the molar mass of 1 mole of a compound. And it's really simple. Okay, for example, if we want to have 1 mole of water, okay, the molar mass is the sum of the atomic weights of all atoms present in the formula. So we know that we have 2 moles of water, and 1 mole weighs 1.01 grams, and then we have 1 mole of oxygen. Oxygen weighs 16.0 grams. We add those together and we get the molar mass of water, which is 18.02, and here's the important part, grams per mole. This means in 1 mole, we're going to have 18.02 grams of water. Okay, so pretty simple, kind of like we did with formula mass earlier. Okay, let's look at a couple practice problems here. So if I have 1 mole of H2SO4, how much is it going to weigh? Go ahead, pause it, see if you can figure this out on your own, and then come back. Don't cheat. Did you cheat? Don't cheat. Pause it. Okay, so let's take a look at this. In H2SO4, we have 2 moles of hydrogen. We have 1 mole of sulfur at 32.07. Remember, I'm just getting these numbers right here off the periodic table. And then I have 4 moles of oxygen. When I do my math, it comes to 2.02, 32.07, and 64, or I add them all together and I get a total molar mass of 98.09 grams in 1 mole. Remember, it can also be called formula weight. So 1 mole contains 98.09. If you're having problems with this, please come see me. It's pretty easy. But please, remember, when you take the numbers off the periodic table, immediately round them to 2 decimal places to keep us all on the same page. All right, let's take a look at this one here. If I have sodium, if I look up on the periodic table, I have a molar mass of 22.99 AMU. Actually, it's not molar masses. I got to change that. It's atomic weight. Okay. The mass of 1 mole now is going to be 22.99 grams. And how many particles in 1 mole? Well, it's Avogadro's number, 6.02 times 10 to the 23rd. If I look at chlorine, it has an average atomic weight of 35.45 AMU, which means its mass of 1 mole of it, same numerical value, different units, 35.45, and it's still 1 mole. Okay, so 6.02 times 10 to the 23rd. Now, if I combine those to form sodium chloride, okay, I'm going to find the mass just by adding these two numbers together, which gives us 58.44 for 1 particle. Or if I want 1 mole of it, 1 mole is going to weigh 58.44 grams. But I'm not going to have the same number of particles. I'm not adding this plus this. No, I have 1 mole of sodium chloride molecules, so I have 6.02 times 10 to the 23rd particles. All right, one of the key concepts that you need to understand or be able to visualize as we do this is what I like to call the Y chart. And a Y chart allows you to convert between things like mass, particles, volume of gas, and moles. So this is something you probably want to have memorized, how this flows. It'll help make things easier. So the central concept here is the idea of the mole. And from the mole, we can convert it into the mass or molar mass. We can figure out how many particles are in a given mass, or we can figure out what volume it is thanks to Avogadro's. So what we're going to see in each of these links is there's something that connects it. Where a connection between mass and moles is going to be the molar mass. Between moles and particles, that's going to be Avogadro's number. And then between moles and liters, this is what we got out from Avogadro's law, we know that 1 mole is going to occupy 22.4 liters. And like I said, you really need to have this memorized. It'll help you flow through these problems. We'll talk about that in just a little bit. Now, particles, there's 3 options up there for particles. When we talk about particles, particles can be an atom, just a single atom off the periodic table. It can be a molecule if we're talking covalent compounds, or if we are talking ionic compounds, we call them formula units. All right, so particles can be one of 3 things. So your unit's not going to be particles, it's going to be atoms or molecules or formula units. Okay, so be aware of that. Your units aren't particle, but it's one of these 3. If we look at this mole volume relations, what we see is that 1 mole is about 22.4 liters, which is about a basketball, or actually about a medium-sized beach ball. Okay, so this is the 3rd connection piece you're going to have to memorize. Okay, that 1 mole is equal to 22.4 liters. All right, so let's talk about the types of problems that you can. There's a bunch of types. You can convert from grams to moles or moles to grams. You can go from particles to moles or back and forth. You can go from volumes to moles. Those are what we call kind of 2-step problems. Now, there are 3-step problems which are a little longer, which if we went from grams to volume, or volume to grams, or grams to particles, or backwards, or volume to particle. Okay? These are what we call factor labeling type problems, or dimensional analysis problems that you're going to have to be able to do all of them. Luckily, once you get them down, it's pretty simple. Okay? We just got to follow our units. So let's look at some of these problems. Okay, the first thing we got to know, as we already talked about, for all problems, we're going to round the atomic weights to 2 decimal places to start off with right away. And then if our answer, once again, we're going to round that to 2 decimal places. So if we have 3 moles of hydrogen, we want to know what's the mass in grams. Okay, so think of our Y chart here. We're going from our upper left our center moles up to the upper left to grams. So that's what I call a 2-box problem. So we always start in our first box with what we're given. Well, in this place, we're given 3 moles of helium. Oops, we can get it show up here. 3 moles of helium. Now we have to get rid of moles. So what we want to get rid of goes on the opposite side. Okay, and what can we compare moles to? 1 mole to its molar mass. So 1 mole of helium weighs 4 grams, and we find that off the periodic table. And so we find out that 3 moles of helium, our moles cancel out, weighs 12 grams. And the important part is that our moles cancel, what we wanted is left on top, so 12 grams there. Okay, what if we want to go the other way? What if we have 120 grams of hydrogen bromide and want to know how many moles? Okay, well, the first thing I have to do is find out the molar mass of that. That's pretty simple. Add those together, and we find that the molar mass is 80.91 grams. Now, it's a two-box problem. Once again, going from upper left, this time grams to moles. So I'm going to create my dimensional analysis table. I always start in my first box with what I'm given, which was 120 grams. Okay, and now I want to get rid of grams, so grams are going to go on the bottom. I'm going to moles. I know that 1 mole weighs 80.91 grams, so I'm going to put that in my last box there. And now I multiply going across and divide on the bottom. So 120 times 1 divided by 80.91 will give me an answer. And we see my grams cancel out. I'm left with moles. So 120 grams of HBr is equal to 1.48 moles. Okay, hopefully you're seeing how this is going. Let's try this one. Now, what if I want to go the other way? What if I want to start with moles and go to the upper right to atoms? Atoms is one of our particles, so think, what's our connection? It's Avogadro's number. This is actually a pretty easy way to go because we don't have to find the molar mass, so we don't have an additional kind of outside math problem to bring in. So I'm going to start with what I'm given. I'm given 0.35 moles of magnesium, and I know that in 1 mole of magnesium, there's 6.02 times 10 to the 23rd atoms. In this case, my moles are going to cancel. I'm left with atoms. Okay, so 0.35 times 6.02 times 10 to the 23rd divided by 1 gives us our answer there. And please note, our units aren't our units are not particles; they are atoms. Okay, try this one on your own. See if you can go backwards. Pause this. Give it a shot, and then come back once you're done. All right. Once again, a two-step problem going from atoms down to moles on my Y chart. So I'm going to start with what I'm given, 7.5 times 10 to the 23rd. This time I want to get rid of atoms, so I'm going to put atoms on the bottom. I know that in 1 mole there's an Avogadro's number, or 6.02 times 10 to the 23rd atoms present. And so this time I take 7.5 times 10 to the 23rd times 1, which I wouldn't do on my calculator, but you get the idea, and divide it by Avogadro's number there, and I should get an answer of 1.25 moles. All right, one last type of two-step problem. If we're going from liters to moles, and this is, once again, a pretty easy one because there's no outside math problem. We know that 1 mole is 22.4 liters. So I'll start, it's a two-box problem, so set my dimensional analysis table up. I start with what I'm given, 10 liters. And I want to get rid of liters, so 1 mole, remember guys, in these type problems, my mole is always going to be 1. 1 mole is equal to 22.4 liters. My liters here are going to cancel out, be left with moles. And so 10 divided by 22.4 gives us 0.45 moles there. Okay. So pretty simple. Now look at this one. This is a little bit farther. We're going from grams here to particles. And you notice there's no direct bridge or no direct pathway. So before I can get the particles, I got to go from grams to moles to particles. So this is going to be what I call a 1, 2, 3-step problem. Okay? We started off just like we did before. What we're given 8.5 grams of sulfur. First thing I have to do is to convert it to moles. Well, I'm going to use my atomic weight, formulate what we call molar mass, right? And so I know that 1 mole of sulfur weighs 32.07 grams. I got that straight off the periodic table. Now I'm at moles. Now I have to go up to particles. I want to get rid. I just got rid of grams, so now I want to get rid of moles. So I'm going to compare everything to 1 mole. So I know that 1 mole of sulfur atoms contains 6.02 times 10 to the 23rd atoms. Okay. Now there we go. Now my moles have canceled out. I'm left with atoms. So mathematically, I'm going to take 8.5 times 1 times 6.02 times 10 to the 23rd equals, on my calculator, and then divide it by 32.07. And I should get an answer of 1.6 times 10 to the 23rd atoms. Okay, hopefully that makes sense. If you let your dimensional analysis work for you, make sure everything cancels out, it's pretty easy. Let's try another one here. What if we're going from atoms to grams? Why don't you try this one on your own and come back with me? It's the same kind of problem we did, just working back. It's going to be a 3-step problem. All right, so we start with what we're given, 8.5 times 10 to the 24th. First thing I have to go, I'm thinking my Y chart, I got to go from particles up here down to moles. Well, I want to get rid of moles, so I know that 1 mole is equal to 6.02 times 10 to the 23rd atoms. And then the final step is to go from the middle at moles, go up to grams, my connection to my molar mass. Well, from the previous problem, I know that 1 mole of sulfur weighs 32.07 grams. Okay? So now on my calculator, I can do it a couple ways. I might take 8.5 times 10 to the 24th, divided by 6.02 times 10 to the 23rd, times 32.07. Okay, there's a bunch of different ways you can enter it. Doesn't really matter how you do it. I suggest you find the method that you like and stick to it each time. That way you can be consistent on it. And you should have gotten 452.81 grams. Hopefully you were able to do that one on your own. Okay, just a couple more practice problems. What about if we're going from liters to molecules? So we're going from the bottom of our Y chart to the top right. Once again, there's no direct connection between liters and molecules, so we got to go through moles. This one's pretty easy because we have 2 fixed variables. So a 3-step problem. We're going to start with 15 liters. My first step is I go from volume to moles, and I know that 1 mole occupies 22.4 liters. Now I'm at moles, I got to go moles to particles. Particular particle we're looking at as molecules. Doesn't matter what the particular unit is because it's an Avogadro's number as our connection. So 1 mole of O2 weighs 6.02 times 10 to the 23rd molecules. I do the math of this and end up with 4.03 times 10 to the 23rd molecules of O2. Okay, one last one. Try this one on your own. Instead of going to molecules, we're going to grams. Go ahead and pause the video again and see if you can make this happen. All right, 3-step problems. Volume to moles, moles to grams. So we start with where we're given 15 liters. We know that 1 mole is 22.4 liters. Now we have to go up to N2, one of our diatomic molecules. And we know, don't forget the 2 in this, that 1 mole of N2 weighs 28.02 grams. Do a little math there and end up with 18.76 grams. Okay, guys, I hope this is starting to make sense with you. If you're a little lost, don't worry. We will go over it in class and do a bunch of practice problems. We'll probably actually do every kind of problem possible with this. But the whole idea behind being able to do these mole conversions is knowing that mole chart, okay, and how that works. So start getting that in your mind so you can memorize it. You got to memorize the moles to particles with Avogadro's number, and then moles to volume, which is 1 mole equals 22.4 liters. And then we know our connection between moles and mass is the molar mass, which you guys should know now how to calculate. Okay, we will do more practice, go over this in class, but if you have any questions in the meantime, please come talk to me. Otherwise, I will see you guys in class. Take care.